Okay, continuing with our condensed formula discussion for 2,3-dimethylpentane. Basically, in the condensed formula, you treat any groups that are off of main chain as substituents by putting them in parentheses. And so off of my second carbon, there are two methyls here. So I put CH3,2CH, and then my next carbon is number 3. It has an H and another CH3. So I put CH and then CH3 in parentheses, so that if you looked at this formula, you'd know that this CH3 comes off of this CH. And then we have CH2, CH3. So that's the condensed formula for 2,3-dimethylpentane. Next is carbon skeleton. Skeleton, obviously, from disclosure from its name, only has carbons in it. So 5 carbons in a row, carbon off of second, carbon off of third, so that's carbon skeleton. And finally, the jagged line drew 1, 2, 3, 4, 5 carbons in a row. This is the CH3 group that comes off of the second. This is CH3 group that comes off of the third, so that's jagged line. Might say that when you guys take organic chemistry, jagged line is going to be your favorite because it's the easiest and fastest to draw. Although it does take time to get used to making sure you capture all the features of the molecule that you're making. Now we're moving over here and we're talking about number 6. And before discussing molecules and show you the molecules you have to make in number 6 of your handout, which is on the very last page of the handout, I'd like to briefly review with you the bond type, hybridization, and corresponding bond angles and geometries. We're only looking at carbon as a central atom, so this summary only pertains to when you're looking at a carbon. So first type of situation we're looking at is something like this. Both of these carbons have only single bonds around them, and there's a total of 1, 2, 3, 4. 1, 2, 3, 4 around each carbon. So this type of arrangement is possible when the orbitals that exist on the outer shell of each of these carbons, which is 1s orbital and 3p orbitals, they all mix or hybridize together, producing so-called sp3 hybridization. The arrangement that these orbitals take in space would be tetrahedral arrangement with a bond angle of 109 degrees. So whenever you have a carbon, consider the central carbon, which sometimes is labeled with an asterisk, which is what you will see in the molecules for number 6. There's one carbon in each of them with an asterisk. That's basically the carbon you're looking at as a central atom. So whenever you have only single bonds around the carbon, you should know that this automatically means bond angle of 109 degrees, tetrahedral shape, and sp3 hybridization. What if we have a carbon that's doubly bonded to another carbon or to an oxygen? Well, then things change because now we have a double bond off of the carbon here. And whenever we have a double bond, as we discussed, we must have a pi bond. So here, instead of all sigma bonds formed by sp3 hybridized orbitals, we now have only 2p orbitals hybridizing with 1s, creating what's called sp2 hybridization. And that leaves on each of the carbons here, or in this carbon, for example, it leaves one unhybridized p orbital that can then be used to create pi bond. We talked about pi bond formation earlier when we discussed geometric isomers. And so in this case, the presence of this pi bond changes the geometry significantly. You're now talking about trigonal planar geometry around the central carbon with a bond angle of 120 degrees, which of course will be resembled in our models and when we look at them. Finally, what if you have a triple carbon-carbon bond? Well, to have a triple carbon-carbon bond, you must have a sigma bond here between each of the two carbons and 2 pi bonds. Now, one thing I want to emphasize, and I always tell this to people multiple times during lab, remember, between any two atoms, regardless what those atoms are, including carbon, of course, you can only have one sigma bond. So here we have triple bond. One of them is sigma, but the other two are pi bonds. So each of the carbons here has two sigma bonds, here and here. Say there could be another hydrogen here or another carbon, but the carbon has two sigma bonds and two pi bonds. So how can triple bond form? Well, triple bond can form if only one p orbital hybridizes with an s orbital, leaving two unhybridized p orbitals to create one pi bond each for a total of two pi bonds. So in this case, you are going to have an sp hybridization of the central carbon with a bond angle of 180 degrees, which means that the geometry will be linear. So let's look at some examples of these molecules. The first one on your list, it says CH3, COCH3. And the carbon next to the oxygen is shown as a central atom. So first, how do we make a plausible structure for it, a structural formula? Well, one thing I want to point out here is the only way this is going to work to satisfy Lewis structure requirements is to put the carbon that's labeled with an asterisk in the middle between two CH3 groups and draw a double bond with an oxygen off of it. If you try to put oxygen next to a carbon within the chain, you're not going to be able to make it work and have proper number of bonds off of each atom. So here everything's what it's supposed to be. This carbon has 4 bonds, this carbon has 4 bonds, this has 4 bonds, and oxygen only has 2 like it's supposed to. This here is a substance called dimethyl ketone, known to most of you as a very common household solvent called acetone, used to remove paint, also is used in nail polish remover. Has characteristic smell too. So what I wanted to point out here is this particular arrangement with a C double bond O between two carbons is called a ketone functional group. So when you take organic chemistry, you have to know all these special arrangements of atoms called functional groups, and ketone is one of them. So here is the model that I made. This, of course, is the oxygen right here, double bond to the carbon, and the carbon has 2 CH3 groups off of it. Might also turn it like this. So what do you see here? Well, you see the double bond, which of course doesn't here represent the true formation of the double bond. It's not two identical bonds, it's two different bonds. One is sigma, one is pi, which is not shown by this particular kit. But what you do see very well here is the bond angle. So this would be a carbon right here that's labeled with an asterisk, the central carbon. This would be the carbon that has a double bond to oxygen off of it. Because it has a double bond, it must be sp2 hybridized. Let me go back a little bit. So it would be this situation right here. Right, so this is my double bond right here between the carbon and the oxygen, and so this would be 120 bond angle, and the shape would be trigonal planar. So that's dimethyl ketone or acetone. So next on your list is a substance that has CH3, then carbon-carbon triple bond, and then another CH3. I did make that one as well. So only carbons in this one, so no red colored spheres here, only black. What do you see? You see 2 CH3 groups on the end and the 2 carbons that are connected by a triple bond. I'm going to turn it around slowly so you can see the triple bond. And this here, either one of these carbons can be considered the central carbon, And for either of these carbons, of course, you have sp hybridization, you have 1 sigma bond and 2 pi bonds, and as a result you have bond angle of 180 degrees and the molecule is absolutely linear. So next one is an alcohol with an OH group, and I have it right here, so we're going to take a look at that one. Position it so we can try to figure out what would be best, maybe like this. So what do I have? I have 1, 2, 3 carbons in a row. 1, 2, 3. I have OH group right here, and then I have CH3 group off of the CH. So here they're showing which carbon is the central carbon. They're showing the one that has 2 CH3 groups, so this one, the CH. Maybe this is a good view. So where I'm holding this carbon here would be a central carbon. Looking at this hopefully shows you that this carbon right here where I'm holding has 1, 2, 3, 4 single bonds off of it, 3 to other carbons and 1 to hydrogen. So I'll let you figure out what hybridization and shape and bond angle this would be. That's up to you to decide. I think you should have no trouble figuring that out. And then a couple more. The next one is C3H7CHO. That would be this one here. So we have 1, 2, 3, C3H7. So this here would be considered propyl from propane. Propane has 3 carbons. Propyl would be this portion right here, and this here would be considered what's called an aldehyde. So you have a carbon doubly bonded to oxygen and 1 hydrogen off of it. I actually did draw that one for you on the last page of the handout. So what I'm holding in my hand right now, let me turn it that way, would be this one right here. So this is more detailed structural formula for it. So maybe I can hold it like this, and you can see this is the CH3, 1, 2, 3 hydrogens, then CH2, then CH2 right there, and then lastly C double bond OH. So total of 4 hydrogens, and then I'm sorry, total of 4 carbons, of course, and then carbonyl carbon, C double bond O, and then H. So this would be considered an aldehyde, and it's butyl aldehyde because it has total of 4 carbons in it. So this would be right there. This here would be your central carbon. That's where the asterisk is in your handout. So once again, your job is to figure out what the bond angle and hybridization and the shape around this carbon is. Hopefully looking at this model, this molecule will help you decide. This concludes our molecular modeling discussion. So I'd like you to use what I showed you in this experiment and all the models to complete the report sheet, then take pictures of each page of it and upload it to Canvas. The due date is shown in your lab schedule. Thank you.